Okay, cool. Should be right to get us going. So yes, Nick Coghlan, Red Hat Toolsmith since 2011, and I've been development lead for a project called Beaker since October 2012. So what is Beaker? It's a full stack integration testing system. So most test systems kind of assume your operating system works. They kind of assume your hardware works. That's great unless you're testing an operating system or you're testing new hardware. And so this is basically a system that Red Hat created several years ago, based successor to a system, the Red Hat test system. So currently the focus is distros that use the Anaconda installer and the Yum package management system for some strange reason. And so yeah, first released as open source in 2009. One of the main things I changed after I became development lead is historically you really couldn't find a lot of high-level info on the public internet about what it was and why you might want to use it. And so that made life difficult for our partners, made life difficult for Fedora. So basically in the last year or so we've been doing a lot of work trying to make beakerproject.org a more useful resource for anybody who might actually be interested in this, and in particular to try and get Fedora using it to try and reduce the cycle times on the Anaconda installer itself and pick up more bugs earlier in the development cycle for Anaconda. So current use cases, we run our own continuous integration in it. So currently we just have a little shell script called patchbot that grabs changes from Gerrit, submits them to our internal Beaker instance, makes sure everything works. At the moment, we don't do any of the pipelining stuff like Zuul does, so we're actually really interested in Zuul because basically for that thing of making sure you have a coherent set of changes and that it works after merging. But main use cases are inside Red Hat. So full integration testing of the operating system, integration testing of other software, compatibility testing for hardware drivers with particular systems, getting new hardware, making sure that that's working correctly with known good operating systems. And then the other thing is once you've got a pool of hardware like that, it's then very useful for reproducing customer issues where they're having trouble with particular pieces of kit. You can get access to those and actually say, oh yes, we can reproduce it and solve it for you. And then the other thing, you can also use it as a general task execution engine. We're working on a bunch of stuff to make it better at that. And then you can kind of use it as a pretend infrastructure as a service system. We really try to discourage people from doing that because it's not very good at it and there's much better solutions like OpenStack out there. So what an actual Beaker instance kind of looks like is if you do a full-scale global deployment, it's kind of complicated and you'll basically, but it looks a lot like a lot of distributed systems. You have a central interface server that end users actually integrate with, that backs the command line interface and provides the web service and provides the main web UI. You then have a bunch of potentially geographically distributed labs, and the lab controllers take care of stuff like the Pixie booting, the controlling power on machines, timing out tests that have just died for no apparent reason, collecting logs, reporting the actual results back to the central server. And then within each lab, you have as many test systems as you want. You can kind of go from a single test lab that just has one or two systems in it up to thousands of machines. And then each lab, you'll need DHCP, DNS, all the basic infrastructure to get servers up and running. Something not shown in the diagram is that if you're doing geographically distributed labs, you're going to need some kind of mirroring system to get your operating system trees out to all the labs. However, if you were basically doing an experimental system or just doing development, you don't do anything that massive. You just use you can just use a single box with a bunch of libvirt virtual machines on it and just do pure virtual testing. That's kind of, if that was all you actually wanted to do in production, you probably wouldn't need Beaker. But it makes development a lot easier because you just have a very simple system, runs on a single machine. So for For actual minimal production deployment, you'd deploy it on bare metal and just do virtualization that way. For development purposes, we actually go one step further and virtualize the management server as well. And so the whole thing can just run inside a libvirt network and be completely isolated from the outside world, where the only thing it pulls in is the installation trees. And that's really nice because it gives you complete control of DHCP and DNS and all that sort of stuff. And you're not depending on anyone else. And the nice thing about starting with that is because of the way the lab controller model works, you can keep that lab controller as your first one and then just start adding more physical lab controllers later. And Beaker will cope with it just fine. So one of the key differences between the way Beaker works and normal provisioning systems work is so something like OpenStack tries to abstract the hardware away from you completely. And so you basically say, give me some compute resources, give me some storage, and I don't really care how you provide it. It's about providing isolation between your people wanting to run software and the people providing your ops infrastructure. Orchestration systems usually go the other direction, and you say, I want that machine over there which has this name. And orchestration systems tend to be very specific about saying, I'm going to do, you're identifying things by name or by UUIDs or by some mechanism you're referring to some specific entity. Beaker is mostly built around the idea of getting access to particular kinds of hardware. So you say, I want an S390, I want an x86 system, I want a system with a disk that's 2 terabytes from Seagate with this model number, so I can test that particular system works with this driver. And that's kind of the heart and soul of what Beaker does that is different from most other systems out there, is that it's about getting access to particular kinds of hardware so you can do full interoperability testing. Unfortunately, this is one of the big holes in our documentation at the moment. We don't really document very well what information the inventory task brings back. If you have access to a running Beaker instance, you can poke around inside the web UI to see what inventory data is available and then figure out how to query it. We've actually just separated out the Beaker system scan component into its own sub-project. And what we're hoping to do is, as that matures as a sub-project and its own documentation improves, we'll actually start documenting better what information it reports, and so it's easy to figure out how you can query for particular hardware without having to look at existing examples. And then the other thing you can do with the distro is that you can basically, when you ask for an operating system, you can either be quite specific and say, I want exactly this nightly build from 20th of December, and I want to install that exact tree and test that tree. Or you can just say, give me the latest stable Fedora 20, and it'll just give you a stable distro. And which one you're doing will depend on the kind of testing you're doing. And so that's basically, and those two basically then defines the resources that Beaker will give you to do whatever testing you're wanting to do. Now, what the job structure is about is basically how do you tell Beaker this is what I am trying to test. And a lot of test systems aren't designed to do multi-host testing. They're designed to basically test on individual systems, or you predefine a job and you just say, run this job and tell me the results, and commit it and run it on particular gates. Beaker's basically designed to instead aggregate multiple test runs into a single event, and you basically tell Beaker, here's the full suite of things I would like you to do. Schedule them all, run them all, and then tell me when the whole thing is done. We'll also report incremental results as individual pieces are done, but overall, it's the case of you can specify large, complex jobs, and Beaker will roll all that up into a single, yes, the whole thing failed or not. So internally, that's all XML driven, but there's a bit more I'll get onto into how you can actually interact with that without ever having to deal with XML yourself. And so anyway, so the simplest possible job in Beaker basically consists of a job with a single recipe set inside it. Within the recipe set, you can have a single recipe, and then that recipe can run one task. If you're running lots and lots of jobs like that, Beaker is probably overkill for whatever you're doing. And so what it's more designed to do is the idea of a recipe set is a recipe set says, here is a bunch of machines that I need configured and running in parallel because I'm going to be talking between them and running a multi-host test. And so what Beaker will do is it'll take care of ensuring that all of those recipes get provisioned in the same lab at the same time, and basically have their timers running in parallel so that you can basically talk between them. And then within a recipe set, then the individual recipes are the definitions of the actual tests. And because we support hypervisor testing, within a recipe you can say provision these virtual machines on that system. And that recipe level is where you specify your host requirements and your distro requirements. And so you can do stuff like ensuring protocols are consistent between architectures and do big endian, little endian testing, all that kind of stuff. So, whoops. What else there? So yeah, and then the job basically, the other thing the job is used to control is, in addition to reporting the results as a group, jobs are also used for access control. And so when you submit a job, you can submit them for automated systems benefit, you can submit on behalf of another user, in which case it'll use that user's permissions if they've given you permission to do that. And the other thing you can do is submit group jobs. And in that case, what Beaker will do is make sure that all members of the group can SSH into those machines, and all members of the group will get permissions on the job to acknowledge or reject the results and indicate whether it's a valid test or not. Because that does happen. Sometimes things go wrong in a lab, you'll get a bunch of tests failing that actually have nothing to do with the test results themselves. And so you can just throw all those results away and say they don't count. So I don't know anybody who likes editing XML by hand. I'm not sure I'd want to know them if they did. And so while we do use a relax-ng schema to formally define what can go into a job and that full job structure on the previous slide, in practice you usually don't want to do that. And so the Beaker command line supports the notion of workflows. And workflows are basically just a way of defining as a command line operation, run this job or run this task on these systems, on this kind of system with this distro. And a few simple ones come with the Beaker client by default, including an XSLT one. But for more complex cases, the general idea is that people write their own workflow plugins. And so most of the definition of what goes into the test will actually be in Python code, generated against XML to send to the server. And then you have command line options to figure out the details. One of the Red Hat ones that we're currently in the process of taking from closed source to open source is the one specifically for Anaconda testing. So that's been around internally at Red Hat for years, and as part of the Fedora Anaconda testing work, that's now moving into the upstream Beaker project. So yeah, and again, a lot more on that in the Beaker docs. The one thing where you will see the actual raw XML is the main web UI supports the notion of job cloning. And so sometimes what you'll have is a case of if a job failed for lab-related reasons, you may just want to rerun it, or you may just want to run it against a new version of the software or whatever, and you can just click a button in the web UI and say, run this again. And it'll give you the chance to tweak the XML. And hopefully I'll get a So yeah, and so the job results page, wishing I'd included some screenshots now, but oh well. So the job details page is basically kind of, at the moment, one of the main ways to get access to all the recipe sets, recipes and tasks that happen in a job. And the jobs basically upload individual results and log details of all the things that happen during the job, including console logs of everything that happened on the server. Because for a lot of, particularly for kernel panics and that kind of stuff, the console log is kind of a rich source of what actually went wrong. In the specific case of kernel panics, Beaker will usually pick it up and just report that the job failed due to a kernel panic. So at the moment, all those details are accessible via XML RPC. We're currently in the process of migrating a lot of our stuff from XML RPC APIs to JSON REST APIs. Those aren't public yet. They're currently still internal between the Beaker client and the server. But once they're stable and we're happy with them, then they'll become a published API on the main web server. And that's actually, Beaker was originally written as a TurboGears 1 application, back when TurboGears was cool. So what we're actually doing at the moment is we're migrating it from TurboGears to Flask and G-Event. And
Promise that's cool.
For now, until it's overtaken by the next shiny thing. But that's actually given us a lot more freedom to do a lot nicer stuff on the web server that TurboGears 1 made a bit more difficult. And so that's actually freed us up to do a lot of things we've been wanting to do for quite some time. And yeah, where we previously had to say, no, that's too hard, we're like, oh, sure, we can do that. It's kind of fun, actually. So the other thing the lab controllers take care of, when you're testing potentially unstable operating systems, it's not uncommon for a server to just go away. And so we do a lot of stuff to try and make sure that net booting will at least work, and so power cycling it will bring it back. And yeah, there's watchdog timers running on the lab controllers every time you run a job, and it basically says if the server doesn't extend the watchdog within a reasonable amount of time, then declare it dead and kill it off. So fairly basic testing stuff, but yeah, and it's one of the main reasons why we try to always have remote power control over any test systems. And then there's also a local watchdog in the default harness. That the problem with the external watchdog is that if it fires, that's it. The recipe's over. It's turning the server off and aborting the job. But there's also a local watchdog that tries to just skip individual tasks if they're taking too long, and that's more under the control of the test authors. Now the other thing this is more for fault investigation rather than continuous integration, which is the case of particularly when systems are failing only on particular hardware. What you actually may want to do is start the job running and then pause it halfway through, or pause it at the end if something went wrong. And so Beaker has various mechanisms in it to let you do automatically reserve the system, and it'll send you an email saying, hey, the system's paused. You can log in, and we set up SSH keys so that you can have log in via SSH. And then basically that lets you do manual fault investigation on hardware that you may not have local access to. And actually do the debugging to figure out, okay, this is how we fix it, and that kind of stuff. Because a lot of the problems in the operating system are hardware specific, and so you can't rely on people having access to those machines in their own office. You need to provide remote access. And then the other thing that this system can be used for is sometimes people, while they're still working on a test case, they just want to be able to tinker with things locally on the machine after it's already set up, and then continue on with the rest of the test. And so that same mechanism lets you do that kind of thing. So it helps with It's not part of the continuous integration as such, but it's something that's very, very useful during test development. And then finally, the manually provisioning side of things is about, well, it becomes a case of once you have this kind of hardware lab, and say you're a support organization, it's really, really useful to be able to get access to those systems for fault investigations for other reasons. And so Beaker actually has a lot of mechanisms built into it for loaning systems to particular users and reserving them temporarily. And that's basically all around that kind of manual fault investigation of, okay, somebody's reported a problem, we don't know what the issue is yet, we're just trying to reproduce it and see if we can figure out what's actually going on. With the hope that you do fix it and you have an automated test that can later run on that same hardware. And so that's basically where Beaker is today. So it's basically if you're trying to do complex multi-hardware things, it's already pretty good, and we're working to make it better. And so this is some of the stuff that we're not currently happy with the way Beaker works, and are trying to improve it. So if anyone's interested, yeah, the actual development process is all Python, almost all Python, except for a bunch of shell scripts. Again, similar to OpenStack, we use Gerrit for the code review. As I said, the continuous integration runs in Beaker itself. But so something we'd really, really want to do or add support for, and we have a design for this, although we haven't implemented it yet, is dynamic virtualization, which is the fact of when you have a test system like Beaker, a lot of the jobs that get submitted don't actually have strict host requirements on them. They're just generic stuff that could run in Jenkins or anywhere. And so one of the problems we have at the moment is a lot of those jobs end up running on specialized hardware that could be getting used for something that really needs that hardware. And it also means we end up having to have lots of generic x86 machines in the pool just to handle some of this load. And what we'd really like to do is farm a lot of that traffic off. We'd like to be able to basically go, this doesn't need real hardware, let's just cloudburst it into OpenStack or Amazon ECS or something like that. And we built an initial version of this about a year ago based on Overt Engine. Unfortunately, we made some wrong assumptions about how Overt Engine reports running out of resources. And so the problem at the moment is that the current dynamic virtualization works perfectly so long as you never run out of dynamic resources. Beaker will currently happily overcommit to dynamic stuff, and then you'll get jobs failing because Overt can't actually run them. However, by the time we realized we'd made this mistake, we'd also been doing further investigation into Overt's capabilities and the path, whether it gave us a path towards image-based provisioning. Because at the moment we do full installs through Anaconda anytime we provision a system. And what we found was that it didn't really. Overt's kind of built around long-lived, high-availability virtual machines that you care for like a precious little snowflake. And that's not what we want. We want the throwaway cattle kind of virtual machines. And that's far more the domain of OpenStack. And so what we're currently looking at is taking our existing dynamic virtualization support, redesigning it a bit to be based on OpenStack rather than Overt. And then at that point, we should get back into that position where once you turn the dynamic virtualization on, any job that comes in that doesn't have specific hardware requirements, we'll just push it over to OpenStack and run it in the generic infrastructure. The other thing we're really working on is currently our scheduler is not very bright. And one of the biggest problems with it is if a system owner puts their system in the public pool, that's it, it's in the public pool. They don't have any privileged access to it anymore, except for the ability to take it out of the public pool again. And the problem with that is it means system owners are more inclined to keep stuff in private pools just for their stuff, And so what can happen is the public pool will be completely backlogged with a big queue of jobs to run, and in the meantime, there'll be systems sitting in private pools not doing anything. And so what we're trying to do is there's a lot of stuff in the grid computing world about how to schedule that kind of stuff in such a way that system owners are willing to provide public access, but they retain privileged use of those systems. So if they have any jobs in the queue, they'll go to the head of the queue for their systems, and so so by having their own systems in the pool, they'll still get their jobs through quickly. But if they're not using them, then those systems can be used to clean up the public pool. And so yeah, that's kind of one of our big focuses at the moment, and that's actually the main criteria before we'll declare Beaker 1.0, is when that scheduler is fixed. That's the definition of what Beaker 1.0 means. Then the other big thing we're working on changing at the moment is, so I mentioned earlier that it's currently very Yum oriented, and the big reason that it's specific to Yum at the moment is that we actually use Yum to install the tasks. That actually causes a whole bunch of problems because there's a Yum repo managed by the main server, and that Yum repo can only have one version of a given task in it, which means that if you want to test the development version of your task, or if you want to keep a specific version of a task around for reproducing an old test, it actually gets really painful and annoying because you have to change names, and it's all just quite problematic. However, there's a wonderful distributed file system called Git that we're basically trying to move the task management over to Git and get the main. Basically, again, there's a design proposal and some initial patches up for that. And once that's done, it'll basically come, we'll still keep the RPM task library, but it will be limited to some basic stuff like running the inventory task and that kind of thing. It'll become a case of it'll be used for support libraries and stuff if people are doing RPM-based testing, but the actual tests themselves should move out to separate Git repos. The other thing that gives is better access control on updating the tests, because at the moment the task library is pretty much a case of if you have access to the Beaker instance, you can update any task. You can update any task in the task library, which is kind of problematic. So yeah, I do have a baby Beaker instance on here, which I will try to run up. But in the meantime, is there any questions? Stunned silence. Yeah.
One of the things that I've seen in large compute clusters that people have talked about is the idea that at some point you can actually, if you need a certain number of resources that are currently allocated to one thing and you need them for another thing, you actually freeze those processes.
Yep.
And then can swap in new processes, run those tests. Is that a solution to the private pool versus the public pool kind of problem?
Beaker doesn't, because it's not an actual infrastructure as a service thing, it doesn't actually virtualize anything. So you can run guest recipes, but we're just basically installing systems from bare metal, running stuff on them, and then throwing them away. So no, we don't have the infrastructure for that kind of thing.
This application, I remember hearing about a new supercomputer where they're actually freezing the process that was running.
Yep.
They weren't doing virtualization. You could easily freeze a virtual container and start up another virtual container on that machine, but there was also talk of being able to just freeze the process and move on from there. But anyway, I don't know if it's useful or not.
Yeah, so the thing for us is we're kind of doing bare metal testing all the way back to RHEL 3. So I mean, there is some of the capabilities on Beaker that only work out to the to the that only work on newer versions and newer versions of Fedora. And so, like for instance, we're hoping to add container support at some point in the not too distant future. But what we will probably do is we'll probably wait until libvirt has native container support and then rely on that. So this is actually the very, oh, hang on. The very bare bones instance I have running on here. So yeah, so it's basically the default view just shows you the systems that are defined in the instance. So I don't actually have any distros loaded into this because I figured conference Wi-Fi wouldn't like the idea of me downloading a Fedora installation. Plus, I doubt this would actually cope with running both the server VM and a test VM. But yeah, so it's basically designed so that you can search for all the devices. Again, this is a baby instance that has no data in it. Search for all the devices, run various things from the task library, if anybody is curious later, I can log into the Fedora instance and show you a bit more interesting stuff. Unfortunately, that's still got the security config for that isn't quite sorted yet, so it's only accessible from the Red Hat network. But I can, if anyone is curious, I can definitely show you that later. Anyway, I'll let you go to lunch. So, thank you all.